Welcome everyone to the wonderful world of 11.9. Well, I guess not really welcome. You've already seen a little bit of 11.9 in the pre-class video regarding this topic. If you haven't watched that video yet, I recommend that you pause this one, go back and watch that, and then come back, right? Because that assumes that we've already seen that video. I will do a quick recap here, but it really behooves you, I guess, to watch that entire video through. You're going to understand a lot more if you've already seen that. So, let's kind of put things in perspective again. In 11.8, we were introduced to these things power series, right? Power series, aka infinite polynomials, right? So they're infinite polynomials, add up a lot of terms together, and we see what comes out. And it's kind of surprising that sometimes, right, you actually do get kind of these nice closed form functions sort of deal. Last time though, in 11.8, we were just given a bunch of power series, right? And we were asked, when do they make sense? And when don't they make sense? AKA, when do they converge and when don't they, right? When do they diverge? In this video, we're going to start actually creating some power series, or really in 11.9 in general, we create our own power series. So before, they were always given to us, and the question was, what is the interval of convergence, or the radius of convergence? Now we are going to be the ones going out and creating the power series. So that's going to be, I think, rather exciting. All right, so a quick recap of what we should have taken away from the pre-class videos for 11.9. The first thing is this theorem right here. This is the big theorem, and I'm realizing that my pencil is not working. I don't know why, so I'm going to pause the video really quick. All right, I got my pencil back working. There we go. Yes, this theorem right here is the big theorem for this entire section. It tells us what the infinite polynomial is, or the power series is, for 1 over 1 minus x. And it's actually relatively nice, all things considered. It ends up being just 1 plus x squared plus x cubed plus so on and so forth, and you just keep on adding, and all of these coefficients in front of the x's, right? There's technically 1x squared, right? It's always just 1 times some power of x, and you keep on getting bigger and bigger and bigger. And how nice. So yeah, this is a relatively simple power series, all things considered. So this is the big theorem. And then from this, we can actually build quite a few things. So with this one piece of information, we're going to try to create power series for a whole lot of other things. And we're going to hopefully see when they converge and diverge and all that sort of stuff. So that's what we did a little bit here. A couple examples of figuring out, now that we know this piece of information, the power series of 1 over 1 minus x, what else can we create from it? And it turns out it's quite a lot. And then we get this very powerful theorem right here, which says that not only can you do some algebraic manipulations, so maybe let's go back here and just talk about really quick. So for these ones, right, we did some like U substitutions. So we did some substitutions. So that's kind of an algebra move there. And then here we also multiplied by something, right? So we did kind of a U substitution, and we also multiplied by something. So again, kind of algebra. But it says not only can you do algebraic things to manipulate these power series, but you could also do some calculus things. That is, you're allowed to take the derivative, and you're allowed to take the integral, and better yet, the interval of convergence doesn't really change that much, at least not the open interval of convergence. So you're allowed to take derivatives and integrals of power series to get even more functions. And so for instance, we did this one here, 1 over the quantity 1 minus x squared, and we figured out its radius of convergence, and notice that we had to take a derivative. And the final example, or examples, right, we did some stuff where we had to do integrals, right? So natural log of 1 plus x, right? If you take the integral of 1 over 1 plus x, you would get the natural log. And so by integrating our power series, we can actually figure out what the power series is for natural log, or down here we do it for tangent inverse. And so yes, we can actually get quite a bit of mileage actually out of one relatively straightforward fact, right? 1 over 1 minus x, this is equal to the power series 1 plus x squared plus x cubed, so on and so forth. But now, right, I'm looking at this again and I'm thinking, is this, necessarily clear, that these are kind of equal? And so I think it's probably a good idea. I have this pulled up on Desmos. I'd like to show you kind of what this looks like one more time here, just so you can see what we mean by these things being equal, because this is the first time we're kind of playing around with these infinite polynomials a bit. And so yeah, let's see that these are actually equal. All right, so here we are at Desmos. I have graphed in blue here this 1 over 1 minus x. So this is kind of a hyperbola looking thing. And you can see there's an asymptote at 1 and all this sort of stuff. And then I have here plotted summing up x to the n. And of course, we can't go on forever with any program. Like this would take, infinite computational power and all this sort of stuff. But we're going to do it for hopefully some very large, and we're going to sum up these and see kind of what we're getting. And so, okay, so first thing, right, when we have it at n equals 1, this would be 1 plus x is what we've graphed here. So this green line is 1 plus x, and you can see that it's basically like a tangent line here for our curve. And then I can increase this, so I can add on the x squared term. So with this, we can see I've added on the x squared term, and maybe this green function is doing a little bit better. Let's add on the the x cubed term. There we go. And when I add on the x to the 4th, and x to the 5th, and x to the 6th, we can see that it's getting kind of better and better as an approximation to 1 over 1 minus x. So I have the first 10 loaded right here. You should also notice that this is okay, but not forever, right? So for instance, down here at -2, the green function and the blue function are significantly different from one another, right? And this is what we allude to when we say, right, an interval of convergence. So it's only on this interval from -1 to 1, right? That's the interval of convergence, or the radius of convergence for this power series. This is the interval right here where the green function and the blue function will be quite close to one another. So, but for fun, let's go ahead and maybe up this. I'd like to, instead of just going up to 10, let's see, allow it to go up to 100. So we can see that our green function, our blue function is getting closer and closer. Of course, if we zoom in on any of these things, right, we can see that they are slightly different. And so for the first 100 or so, we get something like this. And again, you can see that in that interval from -1 to 1, that actually our infinite polynomial, 1 plus x squared plus x cubed, so on and so forth, that this is getting very, very close to the function 1 over 1 minus x, aka, right, this infinite polynomial, this power series converges to the function 1 over 1 minus x on this interval. So that's exactly what we mean, right, when we say this, that 1 over 1 minus x is equal to this infinite polynomial. Again, it's only on this region right here, right, when x ranges between -1 and 1. Otherwise, it's not true. Okay, so that is kind of our 11.9 intro, a little bit longer just because I wanted to show you the pictures and everything. But let's go ahead and move on. And I would like to get into our new problems for today, right? So I've nicknamed this just finding power series, right? We're going to use this fact that 1 over 1 minus x, right? We know what the power series is for that. And we're going to go out and we're going to try to find lots of other power series. Okay, so the way that I like to think about these things, quite often when we're given a function like this, sometimes there's a part that's okay, that's already a polynomial, right? And basically we're going to try to turn everything into polynomials, or infinite polynomials. And so for instance, the 6 on top, I mean, it's not a very exciting polynomial by any means, right? But it is a constant polynomial. The thing that we really have to work with is this 1 over 1 plus 4x. This is the bit that I need to turn into an infinite polynomial. And I guess I'm getting a little bit ahead of myself. I haven't even read out the example for us. It's just I'm excited to get going, I suppose. But we're trying to figure out what are the first 3 non-zero terms of this power series, starting with the non-zero term which has the lowest power of x. Second up, we want to express the function as a power series in sigma notation, summing up from n equals 0 to infinity right there. And then third up, we want to know what is the radius of convergence for this power series. So I don't have to specify the interval of convergence this time. Of course, it could ask for that. This one just happens to ask for the radius. Okay, so again, all of the problems in this section are going to rely on this 1 over 1 minus x. In this case, we're going to plug in something more complicated, like you saw in the video, the pre-class video, right? Let's make this a u so we can kind of substitute things in. And I usually like to carry around the expanded form, and that is 1 plus u squared plus u cubed plus so on and so forth, because this, I have a lot of intuition of what it actually is. I think that these power series are sometimes a bit confusing, especially when you're first getting into them. And so I like to carry around both, and we'll see that actually each one of these pieces helps us answer part of the question. So the summation notation for this, right, summing up from n equals 0 to infinity of u to the n. That's what that great first theorem that we had in the video, the pre-class video, says. Right, it used x's, but we're going to use u's here. Okay, and so we would like this bit right here, the plus 4x, to kind of be the same thing as this minus u. And so we're going to do kind of a mini u substitution. We're not taking derivatives or any integrals or anything like this. So we're just trying to substitute in here. So I would like negative u to be the same thing as 4x, right? And so we can go ahead and maybe rearrange a little bit, and we can see that u is going to be equal to negative 4x. So let's go ahead and substitute in. Everywhere I see a u, I'm going to put in negative 4x. So this is going to be minus, again, negative 4x. So minus a negative, that's going to be the same thing as plus 4x. And that's excellent, right? We're trying to build our power series for this function here. So we're going to also substitute in that negative 4x everywhere I see a u over here. So 1 plus negative 4x plus negative 4x quantity squared plus negative 4x quantity cubed plus so on and so forth. And that's kind of the, again, the expanded view of what's going on here. We can simplify this in just a second. And then as far as the sum goes, again, we're just subbing in everywhere I see a u, I'm going to put a negative 4x. So let's go ahead and take one line to simplify this down a bit. So 1 minus 4x. And then let's see, when I take negative 4 and I square it, I'm going to get positive 16. And when I take x and I square it, I'm going to get x squared. Let's see, when I take negative 4 and I cube it, so negative 4 times negative 4 times negative 4 is going to be negative 64. And when I take x and I cube it, I get x cubed. And we're going to keep on going on forever. And likewise, when I'm writing up my power series, I always split up the constant bit, or really the coefficient part, the part that doesn't have any x's, and the part that has x's, right? So that's kind of getting us in this good habit of writing things like this, right? So you're going to have the piece that's the coefficients. It can have n's in it and all that sort of stuff, but it shouldn't have any x's. The x's should be kind of off to the side there. And so let's go ahead and do the rewrite here. We have a couple things that are both raised to the nth power being multiplied together. We're allowed to distribute our exponents across multiplication like this. So negative 4 to the n times x to the n. And so now you can see my coefficients, my bits that just have n's in it, but are otherwise constant, and the part that has x's, right? These x to the n's. All right, so let's see where we are so far. I have successfully built the power series for 1 over 1 plus 4x. But of course, the one that we would like to build is 6 over 1 plus 4x. So the last step, well, we need to multiply by the 6. So I'm going to multiply by 6, and of course I can do it here. I should also multiply by the 6 on each one of these terms, right? And I could distribute through. So it's going to be 6 minus 24x. Ooh, 96x squared. I'm not having fun here. 64 times 6, 384, I believe. Oops, that's a horrible 3. 384x cubed plus so on and so forth. And then finally, we multiply by 6 on this side as well. And we're going to have 6 negative 4 to the n times x to the n. So again, now this right here is our c sub n's. These are our coefficients for the nth term. And so again, we need that for part B. And then times our x to the n's. So that's our variables. All right, with this, we've actually made it quite far. Let's go back and reread the questions, right? First of all, what are the first 3 non-zero terms of this power series? Starting with the non-zero term, which has the lowest power on x. So of course, this 6 right here has x to the 0th power, right? So this would be the smallest term. Here we have x to the first power. That'd be the second smallest, right? And then finally, we'd have 96x squared, right? And so this would be c sub 0 would be 6, negative 24 will be c sub 1, and 96 is going to be c sub 2, right? Our coefficient that goes along with x squared. So those are the lowest or the smallest kind of three non-zero terms, or the first three non-zero terms, again, starting with the lower powers of x. So this would be my answer for part A. I guess I could go ahead and like highlight this or something. And I brought out kind of what is the C sub 0, what is the C1, what is the C2, because WebWork quite often asks for this. So I want to make sure that you have to split up, right? If they ask for the first three non-zero coefficients, that would be the 6, the negative 24, and the 96. If they ask for the first three non-zero terms, when it says terms, that means it has the x's with it, right? So in that case, we would include the x, and we would include the x squared. So make sure you're just careful with your vocabulary between coefficients and terms. Okay, so that's part A. For part B, express the function as a power series in this form. Well, we've already done that, right? Here's the answer for part B right over here. We have the sigma notation starting at 0, going off to infinity. We have our coefficients, our c sub n's, and we have our powers of x, our x to the n's. So that is the answer for part B. I guess I should go ahead and maybe write here. So this was part A, check. This was part B, check. And now finally, if we wanted to do part C, well, there are a couple of different ways that you can go about this, right? Since we have now the power series, and we're interested in figuring out, right, what is the radius of convergence for that power series, really this is an 11.8 question. So we could go back, put on our 11.8 hats, and we could use the ratio test and all the stuff that we did in 11.8 with this power series here to figure out what the radius of convergence is. So that is certainly a viable option here, but there's actually a bit of a faster way. So remember, this original power series that we used back here, this had a radius of convergence of 1 for u. That is that the absolute value of u should be less than 1. And so if we start with this, that the absolute value of u is going to be less than 1, then we can go ahead and apply our substitution. So in this case, u was equal to negative 4x up here. So let's go ahead and put that in, negative 4x. And we can figure out what the interval of convergence is going to be for x. So let's go ahead and do that. Well, notice that we've multiplied a couple things together inside of an absolute value. We're allowed to distribute the absolute value to each piece. So negative 4, absolute value of that, absolute value of x, this should be less than 1. And so the absolute value of negative 4 is just 4. And let's go ahead, I'm going to write this like this. We'll see why here in just a second. But my last step is I'm going to go ahead and divide by 4. And now we have it in this good setup. Remember, from 11.8, we're trying to figure out this x minus a should be less than r, right? This is kind of the radius of convergence setup here. So we can now clearly see that our center is 0, which, by the way, we could have figured that out just from the form of our power series, right? We can see that this right here is centered about 0. It's not subtracting away anything. And that our radius of convergence is 1/4. So in this case, r would be equal to 1/4. And that would be my final answer. And this is certainly fine work to show on quizzes and exams, all that sort of stuff, in order to get full credit. Or, like I said at the beginning, right, you could also go ahead and use the ratio test on this and calculate out the interval of convergence. That way, it will give you the exact same answer. You'll get that the radius of convergence is still 1/4. It'll take you a few extra steps and whatnot, but it'll give you the same answer. All right, so that is the first question that we have here. Again, getting some mileage out of this 1/1 minus u sort of deal. And I'd like to play the same game here with this one and give you an opportunity to try it out. Let me give you kind of first a hint, and then you should pause the video. Very similar to last time when I went ahead and I factored off the 6, or I moved the 6 off to the side here. I think you should move the x to the 5th off to the side, right? That is already a polynomial. You don't have to worry about that bit so much. The part that's not a polynomial that you need to transform into this infinite polynomial or power series, right? That's going to be the 1/1 minus x squared. So that's the bit you should worry about. And then, of course, just like the other problem, we worried about the 6 at the end. So maybe you could worry about the x to the 5th at the end. So again, please pause this video, try it out, get as far as you possibly can, and then go ahead and unpause, and we'll go through the results together. All right, here is my work. Again, very similar to the last one, we've started off with 1 over 1 minus u. Again, every single problem in today's class, right, is going to start off with this basic fact, and then we need to manipulate it to make it into what we want, right? And so for the first bit, I'm going to go ahead, and my hint to you, right, was to worry about the 1 over 1 minus x squared. And so I think u in this case should be equal to x squared. So I've done a substitution over here, u equals x squared. And so everywhere I see a u, x squared, x squared, x squared, over and over and over again. And likewise here in the sigma notation, instead of u, I've written x squared. And now we have to worry about, right, rules of exponents, right? How do we simplify when we have powers raised to more powers? Well, we multiply, right? And so, for instance, x squared squared, that's x to the fourth, or x squared cubed, that's going to be x to the sixth. And in general, we have, when we take x squared and raise it to another power n, we multiply those together and we get x to the 2n. Sorry, this is a little bit sloppy there. I've also went ahead and in this step, right, I've multiplied through by this x to the fifth, right, in order to create, again, our infinite polynomial that we want here. And of course, when I multiply by x to the fifth on one side of the equation, I should also do it on all the sides, right? So I multiplied this bit by x to the fifth and this bit by x to the fifth. So now everything has these x to the fifths, and this requires one more layer, I guess, of simplification. So we're going to go ahead and simplify one more time just by distributing this x to the fifth to each one of these pieces. And when we distribute that x to the fifth, right, now we have these common bases, the exponents add together. And so I have x to the fifth times 1 is going to be x to the fifth, x to the fifth times x squared, in total there's 7 x's there, x to the fifth times x to the fourth, that's going to be 9 x's in total there, 11, so on and so forth. And in general, right, we're trying to, when we write these power series in sigma notation, we should have our coefficients and we should have our powers of x. And so I would like to go ahead and bring this in and combine it with my other powers of x. And again, that means that we have these like bases, the exponentials, right, the exponents should add together. So we should have 2n plus 5. This is the bit with all of the x's. If we really want to emphasize, right, all of the coefficients are c sub n's, all of them are 1s, right? There are no fancy coefficients next to this. And of course, you can see next to all of these things, we have a 1, a 1, a 1, a 1, right? All of them have 1s next to them. All right, so that answers then parts B, figuring out what the first 3 non-zero terms are, and A and part B. There we go. Speaking's hard. As for part C, well, part C, very similar to our last one, right? We know that in order to use this whole 1 over 1 minus u sort of business, that the radius of convergence is 1. Well, we had a u substitution, right? We substituted, we didn't have just u's, we had x's, and so we should substitute in, instead of our u, we should have x, and then we can take the square root on the both sides of this inequality, and because the square root is an increasing function, we know that we don't have to flip the inequality or anything like this, and so we get this set up here, which of course tells us that the radius of convergence is going to be 1. Again, we're trying to get this set up, you know, x minus a should be less than r. So since we have it in that form, we can just read that r should be equal to 1. All right, so I think this is another, again, kind of, we're still getting used to these things. I'd like to show you this on Desmos, what we've accomplished. So I've graphed it here. I have our original function, this x to the fifth over 1 minus x squared. We can see by our graph here that it has a few asymptotes, so at 1 and at -1. And then I went ahead and I plotted our answer. So that's the green one here that I've plotted. And right now I just have essentially what we're plotting is x to the fifth. And it's doing an okay job of matching up with this blue function, but not spectacular, right? Especially at these kind of ends over here and whatnot, we can see that it kind of differs from the blue quite significantly. But let's go ahead and add on, you know, the x to the 7th term, or the x to the 9th term, and all this sort of stuff. So we can add on the first 100 terms. So not just the first 3 terms, like we did by hand, but the first 100 terms. And we can see that actually this green function and the blue function are darn near indistinguishable, right? Technically they are a little bit different, but man, I'd have to zoom in really, really far in order to see that there's any difference. And again, notice that this works very well on this particular interval. Again, we said something about that the interval of convergence where it actually makes sense is from -1 to 1. After that, right, if we are outside of this interval, notice that the green function and the blue function are significantly different, right? That they do not equal each other. So it's only on this interval of convergence that we have that these two functions are equal. All right, so that's visually what we have accomplished. We have found the infinite polynomial that matches this equation right here, that matches this function right here on the interval from -1 to 1. All right, so with that, let's go ahead and move on to our third problem of the day. As I alluded to in kind of the review of the pre-class videos, right, we can also do stuff with derivatives and antiderivatives. And so I'd like to give you a little bit more exposure to that with these last couple problems here. So now I have a function. Here it is. And I'd like to, again, we're still playing the same sort of game, right? I want to know what the first three non-zero terms are for this power series. I'd like to write it as sigma notation. And then I'd like to figure out the radius of convergence. However, this is starting to look a little bit more significantly different than 1 over 1 minus u. I'll mention, though, that one kind of common mistake that I see people try to make is that they say that this right here is equal to, and then they just go ahead and distribute that 3 to each piece, and they say 1 minus x cubed, and then they go about by making this their u. But sadly, this is not the case. Remember, kind of with these binomials, you'll have to FOIL them all out, and it's a huge pain and everything, but these are certainly not equal. And this is one of the cases where you've altered the problem so significantly that if you did this on a quiz or an exam, I've seen it in the past where a lot of points are taken off for this mistake, because you'll see that the solutions are going to differ so significantly that you fundamentally altered the problem, and so unfortunately not a lot of points are typically awarded for this type of error. So please, make sure to hammer this into your mind that these are not the same, and this is kind of a critical time to make sure that you have that down. Okay, so then, since these are not the same, right, how can we solve this sort of problem? And again, we saw an example of this in the video notes, but this is going to have to do with the derivatives. So let me go ahead and I'm going to first rewrite this. I'm going to pull the 8 off to the side here, and I'm going to write 1 over 1 minus x cubed, quantity cubed. And again, that's the bit that's not a polynomial. The 8 is technically a polynomial. I'm happy with that, but I want to figure out what is the infinite polynomial for this 1 over 1 minus x quantity cubed. And as I alluded to, right, the answer is going to be dealing with derivatives here. And so let's go ahead, and I'm going to start with 1 over 1 minus u. And I'm going to carry around kind of all three pieces. So I'm going to carry around the expanded form, which is, again, this. 1 plus u squared plus u cubed. That's probably enough there. And I'm also going to carry around summing up from n equals 0 to infinity of u to the n. And now I'm going to take derivatives with respect to u here. So if I take the derivative with respect to u on the left-hand side, right, so the far left-hand side, well, let's see, this is all being raised technically to like the negative first power. So the -1 would come down, and then I'd need to raise the remainder, this 1 minus u to the negative second power. Well, that's the same thing as being divided by 1 minus u squared. And then the derivative of the inside. Don't forget the chain rule. The chain rule says I need to multiply by the derivative of the inside, and that's going to be, well, the derivative of negative u is -1. And so we can see that there's actually a little bit of canceling that goes on here, and we're just left with this. So this is what the derivative is on the left-hand side. The derivative in the middle, right? So when I take the derivative of 1, I would get 0. When I take the derivative of u, I would get 1. When I take the derivative of u squared, I get 2u, then 3u squared. That's probably enough there. And in general, right, remember the derivatives are very good over sums. So you're allowed to just take the derivative of each piece. And that's equivalent to if I just take the derivative of u to the n here, well, the n would come down, and I would need to reduce by power by 1. So I have n times u to the n minus 1. And of course, if you start plugging these things in, n equals 0, n equals 1, n equals 2, so on and so forth, you really see that, right? You see, here's the n equals 0, n equals 1, n equals 2, n equals 3, kind of those n pieces, right, are showing up in our actual, expanded view. And notice that the power here, n minus 1, is always 1 less than the coefficient in front. So 2, there was a 3 in front. 1 here, there was a 2 in front. Technically, this is u to the 0. There's a 1 in front. So we can kind of see that, yes, this is all making kind of sense here. Well, notice that we've now have a quantity squared in the bottom, but I want a quantity cubed. So in order to get a quantity cubed in the bottom, I want to take the derivative one more time. So if I take the derivative one more time, well, on the left-hand side, now a negative 2 is going to come down. And let's see, 1 minus u, and negative 2 would go to negative 3. So now I'm dividing by this quantity cubed. And then when I take the derivative inside, right, a negative 1 would pop out. So this is just going to really become plus 2. And so let's go ahead. If I take the derivative in the middle here, well, derivative of 0 is just 0. Derivative of 1 is 0. Derivative of 2u is going to be 2. Derivative of 3u squared is going to be 6u. Oh, you know what? I'm realizing that, look here, it says that we want the first 3 non-zero terms. Well, I've taken so many derivatives that now I only have 2 non-zero terms. So let's go ahead and I want to add one more here. This is going to become a problem eventually anyway. So let's go ahead and just insert one in. So this would be 4u cubed. It's okay to kind of, just as you start doing a problem, you realize, oh, you don't have enough terms. You can go ahead and add one more. So again, if I take the derivative here, I'm going to have 12u squared plus dot, dot, dot. And there, now we're going to have our first 3 non-zero terms. Excellent. When we take the derivative of the right-hand side, this is the one that usually, it takes the longest to adjust your eyes to what's going on here. But again, for each one of these, we're taking a derivative with respect to u. So n is going to be a constant. N is going to be something like this 2 or this 3 or this 4, right? So it's constant with respect to u. It's just along for the ride. When I take the derivative of u to the n minus 1, the n minus 1 is going to come down. And then we're going to reduce our power by 1. So I'm going to get u to the n minus 2. So this right here would be the derivative on the right-hand side. And of course, you can also see this, for instance, if you take 1 times 2 or 2, oops, the other way around. This one's 1 less. So if you do 2 times 1, or if you do 3 times 2, if you do 4 times 3, so on and so forth, right? This gives you 2, 6, 12. That's exactly where these numbers are coming from. 2, 6, 12. So yes, this seems to be working out correct. That's a nice way to just quickly check your work. Okay, so let's see. I think we've done all of our derivative work. Notice I have now this 2 divided by 1 minus u quantity cubed. I guess really at any point here, right, our u is just the same thing as x in this case. So I could go ahead and substitute in, instead of u, I'm going to write an x. And now there's a couple ways that we could go about this last bit, right? We need an 8 on top. We need an 8 and we have a 2. So I think maybe the most straightforward to turn a 2 into an 8 is, of course, multiplying by 4. Now, if I multiply by 4 on this level, right, I have to do it on all sides of the all sides of the equation. So let's go ahead and do those two things in this line. So I'm going to multiply by 4, and I'm going to substitute out, instead of u, I'm just going to write x. So multiply by 4. I'm going to stop writing those zeros. So I'm going to have 2 plus 6x plus 12x squared plus so on and so forth. And then here I'm going to multiply by 4 as well. And again, I'm going to stop writing u, and I'm instead going to write x's. All right, one more line of simplifying, and then we're done. 4 times 2 is going to be 8. 4 times 6 is going to be 24. 4 times 12 is going to be 48. And so on and so forth. And then I'm going to group together. Again, I'm going to bring this 4 inside. And I'm going to group together all of my coefficients. So all the things without x's. So 4n and n minus 1. These would be my c sub n's, my coefficients. And then here we have times x to the n minus 2, right? So all the pieces with the x's there. So again, part A, what are the first 3 non-zero terms? Well, here they are. How do we write it in sigma notation? Here's a good way right here. And then finally, right, what is the radius of convergence for this power series? Well, the radius of convergence is going to come from this original power series here, this 1 over 1 minus u. And so again, For part C, we say the absolute value of u is less than 1. We're going to substitute in, instead of u, we just have x. And so this tells us right here that r is going to be equal to 1. So the big thing that we used here, let me jump back to our video notes really quick. The big thing that we needed to use there is that when you take the derivative or when you take the integral, right, the radius of convergence stays the same. So when you take the derivative or when you take the integral, that radius or interval of convergence does not change. So you don't have to worry about the fact that we took the derivative here doesn't alter the fact that our radius of convergence is still 1. All right, so that is our third problem. In today's class, we only have 4 problems, so we're 3 down, 1 to go. You see we're getting entire pages to write these things on. Here's the last one. X squared tangent inverse of 3x. So let me go ahead and again kind of break this up. There's a part that's already a polynomial. I'm completely happy. Again, we're trying to turn everything into infinite polynomials or power series. So this x squared I'm already completely happy with. The question is, how do I turn this into an infinite polynomial? And then of course I could just multiply by the x squared. So similar as before, I invite you to please pause the video, try this one on your own. My hint to you is that there was a problem in the video notes that was quite similar to this, or the pre-class video notes that was quite similar to this. So you should pause and maybe kind of, if you need a hint, you should look there. But please try to get as far as you possibly can and then come back here and check your answer. All right, I'll see you in a minute. All right, gone off running with this one here a little bit. So let me try to explain my work and what I've done here. The first thing is that kind of with all of the other problems, right, you really saw how maybe it looks a bit like this 1 over 1 minus x or 1 over 1 minus u. So as we go back, right, looking at this one, it's like, all right, yeah, I can kind of see that it would be 1 over 1 minus u. Of course, we had to do a bit of manipulations and all that sort of stuff. Same thing here. Yeah, 1 over 1 minus u, I see how that's useful. And of course, the first problem, 1 over 1 minus u, right, we kind of see how this is used. It's kind of surprising that tangent inverse, right, and likewise these problems with natural logs, that you can set them up and use this 1 over 1 minus u in order to figure out what the power series is for this more complicated function. And the reason why this works is because we're not going to try to build tangent inverse, actually. We're going to try to build its derivative. So when you take the derivative of just tangent inverse, remember the x squared, that's already a polynomial. I'm completely happy with the x squared. You don't need to take the derivative of that as well, but just the derivative of tangent inverse. When you take that derivative, right, here's what you're going to get, right? So the derivative of tangent inverse is going to be 1 over 1 plus, and in this case we have 3x that needs to be squared. So this is on our formula sheet and things like this. And then according to the chain rule, we need to multiply by the derivative of the inside. So again, this is coming back from our chapter 6 days. All right, so this now looks like 3 divided by 1 plus 9x squared, right? Because we needed to square both the x and the 3 there. So we're going to try to build not tangent inverse, but we're going to try to build this thing. This looks a lot more like 1 over 1 minus x or 1 over 1 minus u. And so we're going to try to build this, and then we're going to integrate, right? And of course, if we take the integral of this, we should get back to where we started, right? Because this was the derivative of tangent inverse. And so if we then integrate, that's going to give us our tangent inverse. So that's the idea here. Let's go ahead. Again, we're starting off with 1 over 1 minus u. Right now, we're trying to build the derivative of tangent inverse. So the derivative, and so let's see, I want to have this 1 plus 9x squared in the bottom. If that's the case, then maybe letting u be equal to negative 9x squared, and that way this becomes plus 9x squared, and now we're starting to build again the derivative here. So my u is negative 9x squared, and so everywhere I see a u, I'm going to put negative 9x squared, negative 9x squared, negative 9x squared. So that's all those there. And then finally, in order to build my derivative, it looks like I need a 3. So let's go ahead and multiply by 3. So my next step, I multiplied by 3, and I've simplified things down a little bit. So when I multiply 3 by the negative 9, I get negative 27. When I multiply 3 by, notice this is negative 9 squared, so it has to be 81. So 3 times 81, that's where that 243 comes from. And x squared squared, that's where the x to the 4th comes from. So I just simplified a little bit there. And likewise, on the far right-hand side, I've multiplied by 3, but I've also rewritten this, right? So I have the negative 9 to the nth power, so I have that, and I've multiplied by 3, there's the 3, and then I have x squared raised to the nth power. So when you have powers raised to more powers, again, they multiply. So again, I'm trying to get this, all of my coefficient stuff, all my c sub n's, and then all my stuff with x's. And we'll see that this ends up being very crucial. In fact, it's very nice to have it in this form for what comes next. So what comes next is that we have successfully built the derivative of tangent inverse. So we've built the derivative that is 3 divided by 1 plus 9x squared. So it's the derivative of tangent inverse of 3x. There we go. And so now I want to integrate. So if I integrate, and I'm going to put like little integral symbols here. So if I integrate, and of course we want to integrate on all 3 sides. So if I integrate on the left-hand side, this closed form function, right? Again, we should get to tangent inverse of 3x. Because, right, this bit right here that we built was the derivative of tangent inverse of 3x. So if I do the antiderivative, of course, they kind of cancel out, and we just get back to where we started. Now, if we do the integral of all these things, well, they're just polynomials. So I can integrate 3, I can integrate negative 27x squared, I can integrate 243x to the 4th, and again, we just we raise up our power by 1, and we divide by that new exponent of x. And so there we go. And then finally, this last term, or this last bit over here, this is again where kind of having all of your constants, all of your coefficients, your c sub n's off to the side here is very nice, because now these are all independent, right? They have nothing to do with x. So they're just along for the ride. So they just stay there. And when you integrate x to the 2n, again, you raise up your power by 1. So instead of 2n, you get 2n plus 1. And you divide by that new exponent. So in this case, 2n plus 1. Now this new exponent, the 2n plus 1, right, it doesn't have any x's in it. So notice that I've kind of grouped it over here with all of my coefficient stuff. All right, so we've integrated all 3 sides. Right now, we've finally figured out what the power series is for tangent inverse of 3x. However, my original problem didn't have just tangent inverse. It wanted to throw in this extra bit of a polynomial here, this x squared, and that's fine. We can take care of that at the end, just like we've been doing. So I'm going to multiply through by x squared. So x squared on the left, x squared in the middle. So notice the x goes to x cubed goes to x to the 5th. Again, you have 2 more x's. They're being multiplied, so the exponents add together. There we go. And finally, on the right-hand side here, multiplying by x squared. So you can notice that the 2n plus 1 went to 2n plus 3, right? So again, x squared, 2 more x's. So we should have 2n plus 3 x's rather than just 2n plus 1 x's. All right, so at this point, I have my answer for part A. Right? What are the first 3 non-zero terms? Notice that it was a long journey to get here, right? Each one of these steps was crucial. And then we also have our sigma notation, right? So I have the full power series over here. Again, each step was very crucial. And then finally for part C, notice what we started off with. And again, I should back up one more time and say that you are allowed to use the 11.8 method if you would like. Now that you have this power series, you could use that power series, use the ratio test, and figure out what the radius and interval of convergence is. Or the faster way is that when you use the 1 over 1 minus u, this requires that the radius of convergence of u to be 1. We have our u in this case was negative 9x squared from back up here. I can go ahead and apply the absolute value to each one of these pieces. So the absolute value of negative 9 is 9. The absolute value of x squared is just, well, absolute value of x squared. I can divide by 9. And I can take the square root. And so when I take the square root of 1, I get 1. When I take the square root of 9, I get 3. And so again, we have it in this good form. X minus 0 is less than 1/3. So this is saying that our radius of convergence is 1/3. So this right here is my final answer for my problem here. All right, so as I promised at the beginning, right, we can get quite a bit of mileage out of just knowing that the power series for 1 over 1 minus u is 1 plus u squared, so on and so forth. So all the problems in this section, right, kind of are of this format here. But there are certainly a number of functions out there that no matter how hard you try, you can't write in this form, 1 over 1 minus u. And that is what we're going to be doing in 11.10 that deals with Taylor series and Maclaurin series. So again, these are special types of power series here, and they're going to help us figure out power series or infinite polynomials for any old function rather than just things that we can manipulate to look like 1 over 1 minus u. All right, and just kind of an FYI, I have down here for you a little bit of a bonus challenge here. If you got some free time, find a power series representation in the interval of convergence for this function, and my hint to you is partial fractions. So you can combine some of this stuff together with some of our other previous Chapter 7 knowledge. Anyway, so that's a fun challenge problem. Enjoy, guys. I'll see you out there, and I'll see you next time in 11.10.